you very much, Professor, for this kind introduction, and welcome colleagues and experts to this afternoon session. I'm from the University of Bologna, from the data department, Guglielmo Marconi, and this paper was the result of a collaboration with the DIN departments, the Industrial Engineer department, as well as with AdapTronics, which is a spin-off of the University of Bologna, which helped us in the manufacturing part. So let me introduce the context of the presentation. We will start off with introduction and the main goals. Then we'll talk about the manufacturing techniques for the realization of the rectenna and the characterization of the silicon-based substrate, then followed by the optimization of the nonlinear part, so the rectification side, concluding with some results and future possible implementations. So why we're talking about why we're exploiting flexible substrates? Because as an RF engineer working in wearable electronics, flexibility, washability, and resistivity to bending and stretching is one of the most important requirements for designing antennas, especially when dealing with wearable applications. And most of the materials, such as elastomeric substrates as PMS, polydimethyl siloxane, are definitely really interested in this kind of application due to their properties, as I said, resistivity to bending, stretchability, flexibility, and the fact they're really versatile in terms of manufacturing and realization. For what concerns the manufacturing techniques, like low-cost prototyping techniques, allows not only to create the substrate by using some printing techniques, but also allows to print the metal part, demetallization, so the metal part, by exploiting some conductive ink, allowing not only versatility in terms of geometry, but also adhesion and stretchability. So let's talk about the goal of and the name. The main name that will be redundant will be recurrent in the presentation is rectenna. So what is a rectenna? As the name suggests, is a rectifying antenna. So it's a system that is made by a radiating element and a linear circuit dedicated to the rectification of the received signal from RF to DC. And the idea in this project was to design an antenna on a silicon-based substrate, and one of the main goals was to use one single substrate for the entire rectenna. As we know, when we have an antenna, so a radiating element and a guidance system, we would love to maximize the property by having, for example, a lower dielectric constant for the antenna and a very higher, for example, dielectric constant for the guidance circuit. Here, by using a single substrate, we were constrained on having one single epsilon r. So we played in order to maximize the radiation performance and the guided performance by using different thicknesses. And that actually, the manufacturing techniques came into help because we were able to realize and print a silicon substrate with different thicknesses, in particular 1.8 millimeter for the radiating part and 0.5 millimeter for the part of the circuitry hosting the rectifier part. Here, the rectenna, I'm sorry, here. Where's the pointer? Okay, so the rectenna actually finds the place in here in the schematic of a wireless wire transfer system made from transmitting antenna radiating the signal. The receiving part, as I said, is made by a receiving antenna, the matching network, the rectifying circuit, followed by all the circuitry that deals with the handling of the DC converted power and quantities up to the storage side and the device that needs to be powered. So what we concentrated was the design of the rectenna, and in particular, we start off from the design of from the manufacturing of the silicon-based substrate, and I'm going to describe quickly the manufacturing techniques. So we start off from a two-component, which is the Silpuran 6005, which is a two-component polymer that comes in a ratio, that comes into these boxes. So it's a liquid polymer that needs to be mixed in a ratio 1:1. So the mixing occurs at a speed of 2,000 revolutions per minute, and then subsequently the polymer is cast into a mold. In our case, a mold with two different thicknesses, by using a machine that goes with a speed of 1 millimeter per second. Subsequently, the substrate that comes liquid at the beginning needs to be cooled in open air at the beginning, and then in the oven for like an hour in order to create the cross links, so to establish the bonding in between the silicon particles and to allow the silicon to become solid from a liquid state. So the last part was oven curing of about 100 degrees for 1 hour. That has been found a good compromise for creating a substrate that has a thickness in between 1 and 2 millimeter. So that was for the substrate part, but what about the metallization part? Metallization part that has been exploited takes advantage of the silver ink, so an ink that is made by silver nanoparticles that has been printed on a very thin layer of Kapton. Why are we using Kapton in this case? We're not printing directly on the silicon, because Kapton ensures in this case that the ink doesn't penetrate in the smaller rough surface that could be present in the silicon. So in this case, we're sure that all the passages that we're doing actually stays on the surface without compromising the effective thickness of the metallization. In particular, we do, by using an inkjet printed, we print our metallization, whether it is a patch or the linear part of the rectifier. And in particular, we do multiple passages, which are done. It takes about 15 minutes to realize a patch antenna for our kind, and every passages needs 15 minutes of drying period in order to be able to actually dry a little bit ink and go for the second passage. Every passage of this machine is about 1 micrometer thick. So to achieve a thickness that for our case was about 8 micrometer, it took about like 8 different passages alternated with different resting time. Subsequently, the system is oven cured of about 140 degrees for about 1 hour, and then to protect everything, to make everything waterproof, we cast it with a very thin layer of the same silicon substrate in order to protect the ink that has been printed. So before designing the antenna and the linear part of the rectifier, we needed to characterize the silicon under an electromagnetic point of view, and that has been done by exploiting T-resonate, the resonant technique. What has been done has been created a magnetized line connected to a quarter wavelength open stub resonator, and the thing is, the system has been tuned, and the length has been tuned to resonate around the 1 gigahertz. The system has been measured by using a VNA, and what we did was that by means of iterative simulation, four-way simulation, we have been modifying the epsilon r and the tan delta, so the electric property of the substrate, in order to find a perfect match between simulation and measurement in a range of frequency between 1 to 6 gigahertz. As you can see here, there's quite a good agreement in the range of operating frequency. That can improve for the higher one, but for the operating frequency, that was quite a good starting point. So the first element to be designed was the patch antenna. So the radiating part, and since we had the characterization, we could definitely design it in CST, and has been realized on the substrate of a thickness of 1.8 millimeter. And as you can see here, this is the realization picture. The length of the patch is about 36 millimeter, and the simulation and measurements are in good agreement for the resonant frequency and quite good for the actual matching. Since it's a wearable application, we wanted to investigate the performance when undergoing bending. So the antenna has a measured gain of about 5 dBi and a radiation efficiency that has been simulated of about 30% in the presence of a 60-degree bending, which has been thought to be conformal with an application where the antenna is worn on the arm, for example. The radiation efficiency degrades a little bit up to 25.6%, but still compatible with the with expected performance. So here's a tech-up of the system. We start off from the ground with a copper ground layer, which has been realized by adhesive copper. In this case, we didn't really print it because it was on the bottom side. Then we have the silicon substrate, depending on the part of the rectenna, is either 1.8 or 0.5 thick. Then we have the thin layer of polyimide Kapton of 25 micrometer, on which all the metallization has been printed. The silver metallization or thickness of 8 micrometer, and a superstrate to protect everything and make it waterproof of about 150 micrometer. So here, after designing the radiating part, we needed to perform an optimization, a nonlinear optimization, since we had the rectifier, and the main goal of the optimization was the maximization of the erect to DC power conversion efficiency. So one of the first things that we did was to design in the circuitous environment the topology of rectifier, and the chosen one is a half-wave rectifier in shunt configuration. And as you can see here, the rectifier is derived on the thinner part, as I was mentioning, the thinner part of the entire rectenna. And that's a photo of the prototype with the two different thicknesses. I hope it can be really seen. It's really, really thin here, a little bit thicker here. And the optimization is carried out by the harmonic balance algorithm. The results has been presented here. So we have the prototype that has been characterized and measured. Here we have the RF to DC power conversion efficiency simulated in the range of frequency between -15 dBm and -2 dBm. The receipt power has been characterized preliminarily in order to be able to quantify correctly the receipt power by the antenna. And here we have a measurement of the DC output voltage for the prototype, simulated and measurement in open circuit condition. And there's a slightly difference, but it may be appearance because we have a zoom on, but there is not extremely a big difference in between the measured and simulated one. And so we're quite happy about the overall results. And the one small thing is that when we solder the components for this kind of application, we couldn't use the normal techniques by using soldering and lead as we usually do because of the silver ink, which would have melted. So we were forced to use a conductive epoxy, which was cold. And that is why probably the difficulty in terms of soldering can come along, because it was done by hand in a very precise way, but of course it was not as precise as it could be with standard techniques. So concluding, what I presented today was a preliminary proof of concept of the exploitation of silicon-based substrate to create flexible rectenna at the operating frequency of 2.45 gigahertz. The system has been realized on a polydimethyl substrate, and the fabrication technique has allowed to create a seamless connection of the substrate between two different thicknesses, which have been customized, one for maximizing the radiation property and the other one for maximizing the guiding part. The patch antenna has been realized and measured, and the rectifier has been also realized and characterized, showing quite promising results, which can definitely be improved, and we're aiming to improve that with future implementation, in particular, not only on the overall performance, but pretty much focusing on the performance of the radiating properties and on the techniques for assembling the circuitry, knowing that we need to use a cold way of assembling by using the conductive epoxy that I presented before. Sorry if I've been a little long, but thank you very much for the attention.
Okay, thank you.